Good, thank you. Yeah, I figured as long as I was here in Vienna and you had no one speaking this week, I offered, and thank you for coming again if it's your second time. Yeah, so I'm interested in exchange, wind-driven exchange between marginal seas and the open ocean. Marginal seas are semi-enclosed bodies of water adjacent to continental land masses. So they might be semi-enclosed because there's a narrow strait, could be some topography, a shallow sill, could be a series of islands like an archipelago, some kind of topographic barrier separating this semi-enclosed basin from, say, the Pacific Ocean or the Atlantic Ocean. The scale I'm thinking about is large compared to the baroclinic deformation radius. So rotation is important for these problems. It's not like an estuary, okay, much larger scales. Because of their proximity to continental land masses, there's often a very strong seasonal cycle in buoyancy forcing and in wind forcing. Buoyancy forcing, particularly let's think of the high latitude North Atlantic Ocean. You have the Labrador Sea, the Greenland Sea. You have very cold, dry air masses coming off the continent, storms going over these marginal seas. They extract a lot of heat, cause a lot of mixing in the ocean. That's been studied quite a bit. I'm going to focus more on the wind-driven aspect. There's also a strong seasonal cycle in the winds from these storms. The combination of these wind and buoyancy forcings produces unique water masses in those marginal seas. They're typically represented by very weak stratification because of the convection when the buoyancy is lost to the atmosphere. Dynamically, that's reflected as a low potential vorticity. And you can trace those water masses after they leave the marginal sea on the global scale. At Mediterranean seawater, you can see spreading around the Atlantic. Labrador seawater, you can see spreading all the way across the equator. There's waters that originate down by Antarctica. You can see those spreading north down near the bottom. So they transport heat, salt, and mass on the global scale. So we'd like to understand this kind of exchange between the marginal sea and the open ocean. What I'm going to talk about today, I'm going to introduce the Nordic Seas. There's Denmark Strait to the west of Iceland and the Faroe Bank Channel to the east of Iceland. They both have overflow components. That's what's motivating my interest, but I'm going to cast things in a very general framework. So it's relevant to any number of marginal seas. I'll give examples later. So here's the Nordic Seas. Anybody who was in my talk last week saw this same picture. Here's Iceland, Greenland, Norway. These red arrows depict warm, salty waters coming in from the North Atlantic. They flow cyclonically around the Nordic Seas. As they turn this sort of funky green color, they're getting fresher, they're getting colder, and getting more dense. And there are overflows, indicated by that arrow and this arrow, that are coming along the bottom, go up over these sills, and then spill down into the Atlantic Ocean. So these are, you might think of as the headwaters of the meridional overturning circulation in the Atlantic Ocean. They entrain, yes. This one? On the top. Yeah, this is Fram Strait, and this is the Barents Sea opening. And this is Spitsbergen, yes. Yep. So the Arctic Ocean sits up here. Some of this Atlantic water goes in here. Some of it gets a little more dense. Some of it gets a little fresher, and comes back out. So last week I talked about this a little bit here. Now I'm going to talk about what's going on here. Okay, so in this configuration, we've got these sills defining the marginal sea. Let's ignore about the Arctic Ocean for now. Below the depth of these sills, we have these deep basins. These colors here are bottom topography. So we have deep basins up here. They're regions of closed F over H contours, F being the rotation rate of the Earth, nearly constant for our purposes here. So effectively, these are regions of closed topographic contours. Along the shelf, here and over here, the topographic contours extend to lower latitude, outside the marginal sea. So dynamically, there's two distinct regimes. One is this region of closed topographic contours, and the other one is open topographic contours. And they behave quite differently. So I'm going to be using that as a framework to talk about what goes on in the interior of the marginal sea and what goes on along these open contours. So there's been some work done before. Here's an old 20-year-old paper now by Nost and Isaacson. They were interested in trying to understand the circulation along those closed topographic contours. They derive this expression. You can ignore the details. The point is there's a bottom velocity, V sub B. It's controlled by the area integral of tau is the wind stress. So del cross tau is the wind stress curl. In this configuration, it's assumed to be steady. They're allowing some baroclinic shear. That's a vertical shear in the velocity field. But the bottom line of all of this math is that in steady state, if you've got a wind stress curl inside a closed contour, there's a net Ekman pumping into that region or out of that region. And you've got to close the mass budget. And this does it in the bottom boundary layer. So that V sub B is the velocity at the bottom. This R is a linear drag coefficient. So there's a surface Ekman layer from the wind. The flow spins up to the point where the bottom velocity has a bottom Ekman layer transported in the opposite direction that exactly balances it. And then it's happy and it sits in steady state. This is kind of a companion paper they did where now they're assuming the flow is barotropic. So its velocity is uniform in depth outside of the frictional boundary layers. That's the linear bottom drag term. That's the wind stress term. G is effectively a stream function. The velocities del cross G. But now they're allowing time dependence. This omega is a periodic forcing frequency in the wind stress curl term. So the point here is we can anticipate some competition between drag and time dependence. In this barotropic model, this theory, they compared with a very comprehensive general circulation model, had realistic topography, realistic forcing, it had stratification, and this simple formula did a pretty good job of reproducing the velocity along these closed topographic contours. The barotropic assumption is good for timescales shorter than the time it takes a Rossby wave to cross the basin. Rossby wave crossing the basin adjusts the baroclinic field and it's not barotropic anymore. But if the timescale is short compared to that, then Rossby waves aren't important. At these latitudes, it takes about 10 years for a Rossby wave to cross the Norwegian Sea. I'm forcing things on seasonal timescales, so the barotropic assumption is good. I'm going to take a similar approach to what they've done, but I'm going to have a very idealized configuration, which allows me to get some analytic solutions. So that's what's going on in the interior closed topographic contour region. That's not directly relevant to the sill overflow, which is, I talked about my original motivation. That connects more directly with what's going on in the shelf. So there's two halves to the talk. One's in the interior, one's on the shelf. Okay, so here's my motivation. This is a time series. The blue line here is the strength of the Faroe Bank channel overflow. That was the overflow between Iceland and the Faroe Islands. This is an average seasonal cycle. The large values here mean strong southward flow in this sign convention. So in the summer, June, July, August, the overflow is the strongest, and in the winter, it's the weakest. The magnitude of this is about 0.3 Sverdrup, so 0.6 peak to trough. The mean here is 2.5 Sverdrups. So it's a significant fraction of the mean overflow. This orange line is the velocity just on the north slope of Iceland. So now in the winter, it's strong, meaning strong cyclonic flow in that basin that sits just north of Iceland, and in the summer, it's weak. So those characteristics I'm going to return to with my simple model. A similar cycle in the overflow is found by these previous papers. I'm going to show one in more detail here. This is the Faroe Bank channel overflow. This is a 10-year time series of observations from 1996 to 2016. You can see there's a lot of variability. There's also some lower frequency variability. If you average this into a seasonal cycle, you get this over here, which is essentially the same as the figure I just showed you from that other paper. Strong overflow in the summer, weak overflow in the winter. Interestingly now, if we look at Denmark Strait overflow, the average seasonal cycle is statistically not different from zero. So we've got a strong seasonal cycle on the Eastern Strait, essentially none on the Western Strait. They're both subject to very similar buoyancy forcing. Interestingly now, this is the inflow in Denmark Strait. So this is the shallow water, not the densest overflow water. It's going in the other direction. We see a similar kind of seasonal cycle. If they average it into the seasonal cycle. Now we have strong inflow in the summer and weak inflow in the winter. Very similar amplitude to what's going on in Faroe Bank Channel in the dense water, opposite phase. So my task here is to try to understand these, or at least propose a mechanism for what we see there. Okay, I mentioned that I'm motivated by Nordic Seas, but I'm going to do things in a generic way. This is an example. This is the west coast of Pacific Ocean, South China Sea, East China Sea, Japan Sea, Sea of Cox. These are the winds in January and the winds in July. And the monsoon winds have enormous changes in strength and direction and curl. So these marginal seas are subject to very strong seasonal wind forcing as well. I'm not going to address them here, but that sort of motivates. This is a more general problem than what I'm looking at in the Nordic Seas. Okay, so I mentioned there's two distinct regions, closed F over H contours, and those that extend to the open ocean. There's been some previous work on these that I reviewed a little bit. The nice thing about this approach of integrating along closed contours is the pressure term exactly drops out of the momentum equation because it's an exact differential. And the geostrophic velocity also drops out. Now, if we allow some time dependence, you can imagine you change the winds, it takes the current a little while to change, to adjust to that change in wind forcing. So it takes the bottom Ekman layer a little while to adjust. The surface Ekman layer adjusts right away to the winds. So you can imagine there's a mismatch between the surface Ekman layer and the bottom Ekman layer, where we expect them to balance in equilibrium. So that gives rise to an accumulation of water or a depletion of water within that closed contour. So the sea surface height goes up or down by a little bit. Concomitant with that, there's a big pressure gradient because the sea surface height is changing, and that drives the circulation along the topographic contours. So when there's time dependence in the forcing, we can anticipate a spin up and spin down of flow along the contours. All right, so just to put some numbers to things, here is our Nordic Seas. This red contour is the 850 meter isobath, which is the depth of the Faroe Bank Channel. Denmark Strait is a little shallower, it's about 650 meters. That's going to turn out to be important later on. If I integrate the wind forcing, the wind stress curl, within that closed contour, this is from ERA 5 for 20-year period, this is what you get. You can see two time scales here. There's synoptic events that have 10 sphere drips of upwelling. Strong winter storms go in there, cyclonic wind stress curl. And then you can also see there's a seasonal cycle. So if I average this into a seasonal cycle, I get this. Its maximum pumping is almost 2 sphere drips, and it's about 0 in the summer. So I'm going to force my model with a periodic wind stress curl of about this amplitude. Okay, I'm going to start with some numerical calculations just to kind of describe what the situation looks like, and then I'm going to develop some simple analytic models to explain them. So this is my model domain. This is what I'm going to call my marginal sea. What's contoured here is depth, so it's 3,000 meters deep. I've got a bunch of concentric circles here. My deep basin. There's one strait. I'm going to talk about 2 straits later on, but we'll build our ideas with 1 strait. The model has 5-kilometer grid spacing. It's a hydrostatic primitive equation model, so I'm integrating momentum equations, density equation. It's forced with wind stress at the surface. I have a linear bottom drag at the bottom. It's an F-plane. I talked about why that's okay for this, this region. Now the wind stress is designed very specifically so it's got a uniform curl within that dashed line. So I'm pumping and sucking water in and out of the Ekman layer uniformly everywhere in the interior. Outside of the dashed line out here, the wind stress curl is 0. The wind stress isn't 0, but the curl is 0. So the Ekman transport is uniform. I have a shelf that runs around here. It's delineated by that solid white line. Goes out into this region out here. This funny band that I have outside, the white is a boundary. The funny band I have outside here, I strongly restore everything to 0, the sea surface height, the velocity. So I'm going to get some variability flowing through this strait. The propagation of the waves goes in this direction. So I just want to damp that variability out before the waves can propagate around and come back in on this side. If I had no damping out here, I get shelf waves. They're going to run around here. They're going to come back here, and they're going to go right back in. That's going to complicate what I'm trying to interpret as forcing from within the marginal sea. So I'm assuming that nothing's going on outside the marginal sea. I'm going to see what can happen just from winds within the marginal sea. Okay, I think that's everything there. All right, so this is an example. This is 1/4 of a period into the simulation. This is sea surface height. That's about -10 centimeters in the interior. So I've got a depression. The winds are cyclonic, so Ekman pumping is upward. Ekman transport is out toward the boundary. So I'm taking water out of the interior and I'm pushing it out toward the boundary all the way around. If we look at the pressure or the sea surface height on this outer boundary at 0 here, that's because of my restoring region, right? I'm squishing everything to 0. So this corner is always going to have a flat sea surface height, but we can see some contours emanating from the boundary as we go around. By the time we get over here, there's a gradient in sea surface height between the boundary and the interior. That's given right here. So it's about 4 centimeters, kind of grows rapidly and then grows a little more slowly. This dashed line is the sea surface height along that red contour, which is the edge of the shelf. It varies a little, but much less than this. So for my theory, I'm going to assume that that is 0 all the way along the shelf break, along the edge of the shelf. It's not quite right, but I'm going to argue in a second that I can get away with that. Oops, there. Okay, so if there is a sea surface height change along the shelf break, that implies there's a geostrophic flow across the shelf break, right? There's a pressure gradient there. If we consider vorticity equation, that flow is going to diffuse into the interior, but the topography is steep, right? So that's going to inhibit that kind of diffusion because it's got to stretch. We can derive a length scale like this. Y is the along shelf distance, C is the bottom drag, F is the Coriolis parameter, S is the slope. If we put in typical numbers for each of these parameters, this offshore length scale is 10 to 30 kilometers, so it's pretty small. So even if I'm getting some mass that's kind of leaking over the edge of the shelf, it's going to stay pretty close to the shelf. The main diagnostic I'm interested in here is the flow through the strait. So even if it spills a little bit onto the top of the slope, it's still going to go around and go out the strait. Okay, so here's an example of the structure of the flow in the interior. This is, this got wrapped around. This is at 1/4 of a period. So this is when the winds are the maximum cyclonic forcing. This is the velocity along the topographic contour. So it's very weak in the interior. This is the radial direction. That's the sill depth. And we can see the velocity is nearly barotropic. You can get a hint of a bottom boundary layer there. And it gets faster as you get out towards the edge of the basin. The radial velocity I'm representing as a stream function because it's mostly packed in the surface and bottom Ekman layers. So if I just contour velocity, you're not going to see much. But if I look at the stream function, you can see there's upwelling out of the bottom boundary layer into the surface Ekman layer. You can't see it, but there's a radial transport right there within the very thin surface Ekman layer. But it's not all vertical. There's some horizontal. So some of this water is kind of coming radially into the interior of the basin. If this were the steady balance of those papers I mentioned earlier, all these lines would be vertical. Okay, so now we're going to dynamically decompose this interior velocity field into different regimes. This is the momentum equation integrated along a topographic contour C. Pressure term is gone because it's an exact differential. So we've got the acceleration of the along-topography flow. This is the Coriolis term. It's perpendicular to the contour, so this is the radial flow. This is the bottom drag, and this is the wind stress. So we have 3 different regimes. Near the surface, the balance is between wind stress and Coriolis. That's the surface Ekman layer. Near the bottom, the balance is between bottom drag and Coriolis. That's the bottom Ekman layer. Through the whole interior of the water column, the Ekman layers are tens of meters thick, typically. Water column's 1,000 meters. So the whole interior of the water column, that's small, and the balance is between acceleration and the Coriolis term. So if we Put all these over on the right-hand side, invert for that radial velocity by dividing by f, we can attribute the radial velocity to different terms. So these are the things I showed before. This is the radial velocity due to viscosity. So the surface Ekman layer is hidden. It's right along that top surface. You can see there's a bottom Ekman layer down here, and these are vertical. The acceleration term has this radial component, so it's going from the outside in and also downward. There's a Reynolds stress term, nonlinear terms that I haven't mentioned yet. Turns out my forcing is at such high frequency, I don't have a chance to develop any eddies. I don't develop any baroclinicity. So the nonlinear terms, eddy fluxes, they're all small. So I can ignore those. All right, so now we come back to our equation. I'm going to define my wind stress. It increases linearly with radius at some rate gamma. It's periodic in time. If we integrate this equation from top to bottom, this term, the Coriolis term, is nearly zero because the two Ekman layers and the interior nearly balance each other. The amount that they are out of balance scales like the radius divided by the barotropic deformation radius squared. So for this problem, that term is order 0.1. Okay, so I'm going to ignore that now. And what's left, I have a time rate of change of the tangential velocity. I've got the bottom drag, and I've got the forcing term. So we can just derive a very simple analytic expression for that velocity along the topographic contour. Got the periodic term, got a bottom drag, and the only non-dimensional number here is this alpha. That's the forcing frequency, omega, times the spin-down time scale from the bottom Ekman layer. That's h over c sub d. So if this is large, it means the system's nearly inviscid. Bottom drag is weak, or the forcing frequency is very high. The maximum velocity lags the wind by 90 degrees. If it's small, it's strongly damped, and the velocity and the wind are in phase. In this limit, the solution here is independent of c, and in this limit, it's independent of omega. So for our central calculation, alpha is about 0.4. So we can anticipate it depends on both the forcing frequency and the bottom friction. And then once we have that, we can easily solve for the interior velocity. It's just 1 over f times the derivative. It's given here. This term is the Ekman transport. So this says the interior is proportional to the Ekman transport, the interior transport, according to this ratio. So if it's very high frequency forcing, then the radial velocity is all in the interior, u sub I, and the bottom Ekman layer isn't very important. And if in the other limit, everything's in the bottom Ekman layer, and the interior is not very important. For our calculation, we can, by this result, anticipate that both are important, and that's what we found when we looked at the primitive equation model result. Right, both terms were there. So this is the stuff I already showed you from the numerical model. This theory should be over here. I don't know how it got wrapped around. So this is the tangential velocity, the radial velocity. They should be compared with these. This is the viscosity and the acceleration, and they're compared with these. These compare quite well. These are a little different. This is a little faster here and a little bit noisier here. That's because of the flow coming in over the sill, which is ignored in this theory. So there's some flow across that shallowest closed contour. I'm not going to get into that, but that's what's going on there. But by and large, I think this supports that simple diagnostic. So written another way, the ratio of the interior transport to the Ekman transport is just this ratio. So I've plotted it here as a function of that non-dimensional number. The solid line is the theory, and each of these symbols represents another primitive equation model calculation where I diagnosed the strength of that interior overturning. The size of the circle represents the period, so this is 1 month forcing, and this is 5 years period. And then the color represents the strength of the bottom drag. So I'm varying a couple of parameters. They compare reasonably well here. I think this offset is because to define alpha, I need to define a depth. So for simplicity, I took it to be the maximum depth over 2 for all the calculations. But that's not really right. If I pick a shallower one, this solid line shifts to the right because these are shallower features. And if I pick the deeper one, it shifts to the left. So I think that's why we see this systematic shift to the right and left. But that's okay. I'm not too worried about that. Okay, that's it for the interior. I'm not going back to it. Anybody have any questions about that? Okay, good. Moving on to the shelf. Now, there's a couple of differences. By design, Ekman pumping over the shelf is 0. Could have added some in there that just add another forcing term. I wanted to make this simple as I could, and I really wanted to see if the flow through the strait was related to what's going on in the interior of the marginal sea. So all the Ekman pumping is concentrated right at the boundary. I've got Ekman transport hitting the boundary, and you get an arrow upwelling or downwelling there. There are no closed F over H contours now because they go out to the rest of the world. So I can't use that same circulation integral approach. The adjustment time scale on the shelf is very fast. Time it takes a shelf wave to go around the basin, which is a few days, compared to my seasonal forcing time scale. So the mass budget on the shelf is always closed. And sea surface height isn't changing on the time scales that I'm interested in. The acceleration term, this interior use of I term that was important in the interior, now it's very small because H is the depth of the shelf, which is order 100 meters, instead of the depth of the interior, which is 1,000 meters. So I get to ignore that term. And now I'm going to develop a simple model for what's going on in the shelf. First, I want to describe it. So here's my domain. I'm going to look at the velocity over here on the shelf along that western side. The along shelf velocity over the shelf is nearly uniform across the shelf. That's consistent with Dave Shinadi's rest of wave topographic theory. So I'm showing the average velocity along that section. It's a function of depth and time. This is along the shelf. You can see it's nearly barotropic. There's a little bit of a bottom boundary layer. It's going to the south when the winds are cyclonic. So the flow around the shelf is cyclonic. It's going to the north when the winds are anticyclonic, same bottom boundary layer. This is the cross shelf. I'm again representing as a stream function. I've got a surface Ekman layer, bottom boundary layer, and not a whole lot going on in the interior. That's that use of I that I ignored. For some reason, the anticyclonic phase has got a little bit of transport in the interior. I don't understand why that's there. Okay, at this location, the cross-shelf transport nearly balances within about 10%. You can see that a couple of these contours hit the bottom, which means there's a net cross-shelf transport, but they nearly balance. That's something I'm going to return to later. So here's my simple model. This is my strait. This is a piece of the boundary of the marginal sea. The way I've drawn it here, the wind is blowing from right to left. So this is upwelling favorable winds. There's an offshore Ekman transport. Here the velocity is 0. I've got some offshore Ekman transport, so it's got to be balanced in a closing the mass budget sense. So I develop an along shelf flow. That along shelf flow has associated with it an onshore bottom Ekman layer transport. So I'm going to assume the pressure anomaly is 0 here, below the wind parallel, and I'm going to develop a model just relies on closing that mass budget. The thing I don't know is this V sub s, the velocity along the shelf. Okay, so this is my mass budget. The along shelf divergence of the velocity times the depth and width is balanced by the difference between the offshore or onshore Ekman transport in the surface minus that in the bottom. The bottom depends on the velocity. So this is a simple equation we can solve. Velocity along the shelf varies periodically. This coefficient, tau over rho naught C sub d, that's the velocity for which the bottom Ekman layer transport exactly balances the surface Ekman layer transport. When y is 0, the velocity is 0. That's right at the inflow, right? So I can't have any flow going to the left of that. And it adjusts to this velocity and magnitude over this length scale, L sub y. L sub y, we can interpret, whoops. Sorry, I pushed the wrong button there. There. L sub y we can interpret as F naught times L. That's roughly the shelf wave speed times the damping time scale, this depth of the shelf over C sub d. So that's the distance a shelf wave propagates before it gets damped by bottom friction. We can, let me see that, yeah. So this is what I just said. Now, once we know the velocity, we can solve for the sea surface height because we're assuming that the velocity is uniform across the shelf, assume it's in geostrophic balance. And I'm going to test this now in the numerical model. Okay, so this is the fraction of the Ekman transport, psi sub e, driven by the wind stress that's provided by the along shelf flow, that's y sub s, transport along the shelf compared to the transport in the surface Ekman layer. If this number is large, so if the basin is large, if the damping length scale is long compared to the perimeter of the basin, we're out here. That says all the Ekman transport, it's getting pushed into the interior of the basin or expelled from the basin, is coming from or returning to the open ocean. It's not from within the marginal sea. At the other end, down here, it says that everything's equilibrated. The onshore and offshore Ekman transport balance, and all the overturnings within the marginal sea, and doesn't really know the open ocean's there. You can imagine if you have a huge marginal sea and a tiny little strait a long ways away, marginal sea doesn't know the strait's there. But if you got some friction, it might. I'm sorry, if you have no friction, it might. So in one limit, this is the inviscid model of John Allen. But I think friction is going to be important. So here's the takeaway. If you remember nothing else from today, this is the main point. So flow from the shelf comes from outside the marginal sea through the strait. So let's say that was all that was going on. You're just sending water out, you're just bringing water in. The magnitude of the Ekman transport's on the order of a spheredrup, if you remember what I showed for the Nordic Seas. If you have a spheredrup imbalance in the mass flux for a year, seasonal forcing timescale, the sea surface height is going to change by something like 1 to 10 meters, depending on how big your basin is, right? That's not going to happen. The sea surface height is just too rigid. You get a little bit of a depression, there's a big pressure gradient, and that drives a flow. So in order to balance mass, the flow going out the strait on the shelf has got to be balanced by a flow coming in the deep ocean, or flow going in on the shelf is balanced by flow going out in the deep ocean. So if we put in typical parameters, this length scale is on the order of 1,000 kilometers, which is on the order of most marginal seas, like the Nordic Seas or Mediterranean's bigger than that, but it's telling us that this length scale is important. So that says a significant amount of the Ekman transport into the marginal sea interior is coming from or being returned to the open ocean. And that also requires a transport in the opposite direction, and that goes through the deep strait, as I'll show. Okay, that's the take-home message from the talk. So let's look now at the primitive equation model. Here's my marginal sea. I'm calculating the net transport across the strait right there. This is depth, this is time, 1 year. And when the first half, between 0 and 0.5, the winds are cyclonic. So I've got upwelling in the marginal sea, pushing water toward the boundary. In the upper ocean, I have flow to the south, flowing out of the strait. In the deep ocean, I have a sill up to 650 meters. In the deep ocean, it's going back into the marginal sea. If I integrate this transport at any time, it very nearly balances. Transport, the magnitude of this, if I kind of fit it to a periodic wave, it's about a half a spheredrup, or about 60% of the Ekman transport. Okay, so this is what I just showed you. But now if we look at the velocity, this looks very baroclinic, right? It's coming out at the top, it's going in at the bottom. If I look at the velocity across the strait at that time, which is the maximum exchange, it looks like this. That's the southward flow. It's shallow. My shelf disappeared, but that's just a detail. So this is the shelf flow, it's shallow. This is the return flow in the deepest part of the strait. They're both very nearly barotropic outside the bottom boundary layer, right? So the whole exchange is barotropic. Everything's too fast for baroclinicity to be important. And this transport very nearly balances that transport. But this is directly connecting what's going on up here on the shelf, what's going on down here in the bottom of the strait. This is just kind of an interesting detail. I added a tracer within the marginal sea, a passive tracer that I restored toward 1 below the sill depth. And this is the transport of that tracer, the value of that tracer in the strait. And we can see here, some of that water that's coming over the sill came from below sill depth. So there's some aspiration in the marginal sea. I'm flushing out the deep marginal sea. And that kind of makes sense. I'm pumping water down on very short time scales. There's nothing to attenuate that. It's an F-plane. There's no Reynolds stresses, so the W just pushes the water down, all the way down. And it's got to close the mass budget in those deep basins, right? If I'm pushing water down, it's got to come up somewhere. And it does. It comes up along the edges, and some of it spills out over the strait. I showed on the slide, I didn't mention, these are all stratified numerical model calculations. Turns out stratification isn't very important, but it's in the numerical model. It's not in the theory. So everything's just too fast for stratification to be important. Okay, so let's look at some of the details here. This is the theory for the sea surface height along the boundary. That black line is diagnosed from the primitive equation model. This red line is an exponential fit. There's 2 parameters, this eta naught and this L sub y. In the model, eta naught's 3.7 centimeters. In the theory, it's 3.9. The model diagnosed is 2,200. The theory, it's 2,000. So they agree surprisingly well. But that's just one calculation. Maybe I got lucky. Maybe I was devious and designed things that way. So now I'm redoing the model with a whole bunch of different calculations. I varied the bottom drag, stronger and weaker. I varied the shelf width, wider or narrower, and shelf depth. And the wind for all of these is the same. Now, there's a whole bunch of pairs of curves here. The dashed lines are exponential fits. The solid lines are diagnosed from each numerical model calculation. You can't really tell the details, but the basic point is they're all essentially exponential. So I've diagnosed those 2 parameters from the exponential fit, and I'm comparing them with the theory. The first one is this long slope decay scale, L sub y. This is from the theory, this is diagnosed from the model. There's reasonable agreement. These down here disagree a little bit. There's actually 3 of them stacked on top of each other. In each of those, the shelf is either very narrow or very shallow, or friction's very large. So those are very viscous shelves. And I think in my model, more of the transport is kind of bled off the shelf break, so it's over the top of the slope. So it's effectively making the shelf a little wider. So the numerical model is behaving as though the shelf were wider than the theory thinks it is. I think that's why those are off a little bit. Now this is the sea surface height anomaly, this eta naught. Not great agreement. The frictional ones have the wrong slope, but they all get the right basic parameter dependence. I've forgotten which are which now. Yeah, so the width is green, the depth is magenta. So the width, at least they have the slope in the right direction. This is that central case I've been talking about in detail, and those are bottom friction. The right order of magnitude, kind of getting the right parameter dependence. Now this is the transport through the strait. Most of these agree pretty well. That's that little cluster where I had the decay scale wrong in the model. But other than that, they agree pretty well. If I then instead put in the theory of the decay scale diagnosed from the model instead of the one predicted by the theory, I get these little blue squares, and most of that discrepancy is gone. Now they agree pretty well. So I think the problem with these is that my model is just too viscous on the shelf. So I get the decay scale wrong. Okay, I motivated this with the Nordic Seas and 2 straits, and I was really interested in this dichotomy between the transports west and east of Iceland. So now I'm going to return to that. Here's my marginal sea, and now I have 2 straits. I will somewhat boldly call that Denmark Strait and that Faroe Bank Channel, and this Iceland. Now I'm looking at the transport through these straits, the Western Strait and the Eastern Strait, and it looks like this. So I get a large seasonal cycle in the upper ocean in Denmark Strait. That's consistent with the observations. But I also have a large transport down here in the deep part of Denmark Strait and a weak transport in Faroe Bank Channel. That's not consistent with the observations. This makes sense that most of the transport's here because, remember, the transport's driven by the sea surface height anomaly, and that's essentially the integral of the wind along the boundary. So my pressure anomaly is 0 there, and 0 there. The two inflowing, in a wave sense, inflowing pieces of the boundary. So this one has this entire boundary to accumulate sea surface height anomaly, and this one only has the size of Iceland, right? So I don't get much going on here, and everything going on over here. Doesn't really know that strait's there. There's also a circulation driven around Iceland, which is why these are not symmetric, but I'm not going to talk about that. Okay, so what happens now? In the real world, Fairbank Channel is deeper than Denmark Strait. So now I'm doing this again, and now I made this 850 meters. This is still 650 meters, and these are the same two diagnostics. The upper ocean still going through the Western Strait. Makes sense for the reasons I just described. But now the deep Western Strait has a very weak seasonal cycle, and the eastern Western Strait has a strong seasonal cycle. Now we're getting this seasonal cycle here. So the outflow, this is to the south, the outflow is strongest in summer. The inflow, and it's weaker here. The inflow is strongest in summer and weakest in winter in the Western Strait. So that's consistent with what I started with. Remember the time series of the current meters. And the shift from the Western Strait to the Eastern Strait is because this strait is deeper. At a barotropic signal, it's just going to follow, I think, the deepest pathway. That's not predicted by the theory, but I think it makes sense. Okay, so that's the story. Ekman pumping in the interior regions of closed F/H contours is balanced by a combination of flow in the bottom boundary layer and flow in the interior. And the decomposition, how much is in one or the other, depends on this non-dimensional number. That's the frequency times the damping time scale. High frequency or weak viscosity, it's all in the interior. Low frequency or strong damping, it's in the bottom boundary layer. The transport into the basin interior, some of it comes from along the boundary, some of it comes from within the interior in the bottom Ekman layer. Determining how much just depends on the size of your basin or the distance between straits, if you have more than one strait, compared to this damping time scale, or damping length scale, and that's the distance a shelf wave can propagate before you damp it away. So I had some simple theories, I had some idealized models. I think they compared reasonably well, sort of supports the basic story. But of course, I had a really simple configuration here, and I ignored some things that might be important. So it's difficult to test these things, say, in the real Nordic Seas, because the shelves are variable depth, they're variable width, the winds are not nice and uniform and cyclonic, right? They're time dependent, they're sometimes over here, sometimes over there. I have a linear bottom drag. I don't know that it's uniform, I don't know that it's linear. So this is really a conceptual story, not something I can test directly, but qualitatively, what it predicts for the Strait transports, it's got the right phase, it's got the right magnitude, it's got the right geographical distribution. I've also assumed things are barotropic, but if we consider either lower latitudes or lower frequency forcing, then baroclinic Ross waves are important, and especially for my story in the interior closed F/H contours, this theory will be incomplete. I won't say it's wrong, but it's not complete. I would have to take those waves into account. So, time for any questions.